Okay, here we go. So for today, we're gonna play a little game. Okay. Our game. Oh yeah, you love it. No, I don't. Yeah. So our game is called Calculus Jeopardy.
Can we turn the fan around? It feels nice.
Uh, I mean, kind of. Math is just a game, essentially.
Life doesn't look good.
All right, so we have everybody's attention, please. Okay, sorry that took so long, but technical difficulties. All right, so let's get going. So how do we play Jeopardy? How do you play Jeopardy? Well, I don't have questions. Okay, there you go. Good. I give you the answer and you provide the question, right? Okay, so
What is chicken? What is 6x?
okay, so the answer to this question is really what or is the derivative is 3x squared. What is the question?
What is the derivative of?
What's me in?
I do have to do it backwards.
Yeah, exactly. Yeah.
So x cubed.
That's it. Okay.
How do you do
Okay. Everybody get it? Okay. This is Calculus Jeopardy. All right. Let's try another one. Sort of. No, it won't. It won't. Okay.
Derivative is sine x. What is
What's it gonna be? Negative cosine x. Excellent.
or what is it?
Okay. Those are correct. Those are correct. Now let's go back to the first question. Somebody give me another answer that's also correct.
The first
Yeah.
one?
Mm-hmm.
3 times
So x cubed works. What's another one?
1 over x to the negative.
Well, no.
Oh.
Too complicated.
But it works,
I'm
right?
not wrong.
So what is it?
X cubed plus
X cubed plus 10. Awesome. Okay. Right.
It was something that requires it.
Okay, so the derivative of a constant is always 0. Hey, this is too much talking. I'm going to have you raise hands, please. Okay, question. Another one? Another one. Say it again.
X cubed
Plus n. Okay. Now, this is good. So what Alex is doing, he's trying to give us an answer that represents all possible answers. Okay, and we're going to do that. So really, all of this stuff can be combined. This is good. You guys are awesome. So all this stuff can be combined into the single solution, x cubed plus c. What do you suppose c is? A constant. Yes. C could be any constant, right? So it's,
essentially say x cubed plus
well, no, infinity is not a constant.
okay, true.
You can say x cubed plus a Google. You can say x cubed plus pi. Any of those would be okay. X cubed plus any constant would work because when I differentiate it, I'm going to get back that answer, right? Plus 0. Okay? Question. Exactly. Yeah, the constant could be negative. It is, I believe, 27.
It's Haley's birthday.
Okay. All right, so the game we're playing, Calculus Jeopardy, Delaney guessed it. This is Okay, now, when we get an answer like something like this, like x cubed plus c, what does that look like? You know, that looks like a, what we call in calculus, a family of curves, because c could have, they all look essentially the same, right? They all look like x cubed, but what do I do to a function if I add a constant to it? Okay, I vertically offset it, right? That's all I'm doing. So if I were to graph this, it would look something like, let's say I'm going to draw the one where c is 0. That'll be sort of our parent function, right? If c is 0, it just looks like that. Okay? So that would be c equals 0. What does it look like if c is 1? Well, if c is 1, I'm just going to move this up by 1, right? And so it's just going to look kind of like that, right? If c equals 10, it would be up there. If c equals pi, it would be, you know, somewhere in here-ish, right? You get the idea? Okay, so it's a family of curves. There are an infinite number of curves, but they're all represented by that solution. Okay, this is what we're going to come to call a general solution of a differential equation. That sounds fancy, and it is. That's really all we're doing is anti-differentiating. For now, though, well, let me define that term. Differential equation sounds just so impressive and scary, but really all it is a differential equation is just an equation with derivatives. Maybe one derivative, maybe more. That's it. Okay? So for example, we could take the differential equation y prime equals 2. And that's really just like playing calculus Jeopardy, right? Because if we want to solve a differential equation, the way we solve a differential equation is by undoing the derivatives, right? So we're going to solve for y like we normally would. When we solve other equations, we isolate a variable, right? It's the same kind of thing. We want to figure out what y is based on the derivative function. So play calculus Jeopardy for me. What's the answer? So y equals 2x plus c. Good. Now that is our general solution. It's our general solution because it represents all possible solutions, right? What if we know some additional information, though? What if we know, for example, that, let's say, we know that this is the case, but we also know that when x equals 0, y equals 2. Okay? So we know that that has to be true. How does that help us? Because it allows us to solve for the constant, doesn't it? Right? So if we plug this information in, what do we get? Well, we get 2 equals 2 times 0 plus c. So what's the value of c? 2. So c equals 2, and then we end up with the solution y equals 2x plus 2. Okay, now this is what we call a particular solution, because it's one particular trajectory out of this whole family of curves, right? If we were to graph this thing, I mean, we can't graph them all because there are an infinite number of them, but it would look just like the graph we had a second ago. What this really represents is just a family of lines with a slope of 2, right? And the y-intercept is going to vary, right? That's the value of c. So if I were to graph this, let's see, it's going to look kind of like, so here's 1, going through the origin with a slope of 2. So there's 1, right? Here's another one right here that goes through 1 with a slope of 2. Here's another one, the slope of 2. And this one is the winner because it's the one that goes through the point 0, 2, right? That's really all that is. Right? It goes through the ordered pair 0, 2 corresponds to a point, which is right there. So that's the one that corresponds to the particular solution. Yes, ma'am.
What kind of real life situation was he in?
Okay, this is huge. This is in virtually every real life situation. So in my career, what I did is a lot of times in physics is we would solve differential equations based on boundary value problems. Like, so for example, if we wanted to see if there was some function that was, let's say we were trying to solve for the vibration of a violin string or something. Okay, we would know some things about it. We would know where the amplitude had to be 0. We would know maybe how fast it was vibrating, so we'd know something like dy dx, right? And then so we could build a differential equation from that. And then by solving the differential equation, we could come up with a mathematical model that would model that violin string's function of time. So that's just one example of something you could do. But there's so many of them. Using the antiderivative. Because and this is, I want you guys to just think about this. This is not something we're going to do this year. But as you look ahead into your futures, if you go into math or engineering, or if you want to just have a strong foundation in math, which makes you super, super marketable and desirable, and even if it's not a physical science field you're going into, say you go into, maybe you go into, like social sciences, okay? If you go into social sciences, but you have a strong math background, all else being equal, you're the person that's going to get the big grant in college. You're the one that's going to get the best advisor to work with. You're the one that's going to have opportunities to do graduate work while you're an undergraduate, and you see what the trajectory is. I mean, so you want to pursue math. When you going forward, the kinds of problems that you'll solve, like in physics or engineering or in music theory or in whatever, it's easier to build a problem based on a differential equation. We can set up, that's relatively easy to do. You can construct the differential equation from stuff you know about the behavior of the situation. It's very difficult to go directly to the actual function, right? So what we do is we construct a differential equation, and then we do calculus to reverse engineer that to come up with the function, which is the answer, okay? It's a long answer to a short question, but that's kind of gives you just a brief glimpse of sort of where this goes. So, okay, so then what do we call this? So this was a general solution. If we attach this particular condition, so we attach the particular condition that the function is equal to 2 when x equals 0, right? Then that leads us to this, which is what we call the particular solution, or a particular solution. Do you get that? See the relationship? A particular solution ends up being a specific trajectory out of the family of all infinite solutions that matches a specific condition. So there could be, yeah, there could be more than one. If we said we're looking for all the solutions where this is true, and maybe also where x equals 4 when y equals whatever, right? That's going to give us a different one, right? Okay, typically you only deal with one at a time, one per problem. Okay.
Maybe like you had some issue, like maybe a quadratic equation, something, would it be possible to have like 2 particular solutions that fit the same specific point?
With the same point?
Yeah.
No, because one thing about families of curves is they don't intersect. Families of curves, like if I were to draw all of these curves are straight lines, but when we say curve in math, we just mean function, right? We don't actually have to curve. So these are all going to be parallel lines. Parallel lines never cross. If we went back to the previous picture that I drew, this family of cubic functions, they also would never cross, right? We could have families of non-functions like concentric circles or things like that, right? But they're still never going to cross. Okay, does that make sense? And I don't know if I should say that. It's possible families and curves could cross in some unique circumstances. So the ones we're dealing with won't. Let's just say that. Question? Okay. So let's take a look at an example for all you physics types, and this will work for everybody. Let's do some interesting stuff here. We learned a bunch of kinematics equations early on, right? You might have wondered where those came from. We can find them so easily solving differential equations. Okay, we got to remember a couple things though. Remember that if we say S is position, right? So S is, and we could even make it simple and make it on a line and call it X if we wanted to. So if S is position,
Mr. Owen.
yeah.
The kinematic equations are like position.
Yeah, position, velocity, and acceleration, right, as a function of time. Time is the kinematic parameter that links them all together. We track all of those with time. People that are in physics will be pretty familiar with this idea. So S is position, V is velocity, and A is acceleration. Okay, so here's what we know. We know that the definition of velocity is ds dt. It's just the rate of change of position with respect to time, or the derivative of position with respect to time. Okay, acceleration is what?
Derivative of velocity.
Okay, dv dt. Yeah, it's the rate of change of velocity with respect to time. Which in terms of position would be the derivative of the derivative, which is a second derivative, right? That's a weird, we write that one strangely. We write it as d squared s over dt squared. It's kind of a weird terminology, but that's really just a double prime. That's all that is. Okay? That's a second derivative. Okay, so let's start off. Let's be like Newton. How about? We'll be Newton, because the reason he developed calculus was largely to solve problems like this. Okay, so we could observe by rolling objects down ramps, for example, to slow down the acceleration of gravity, we could observe that the acceleration of gravity is constant and it's about 9.8 meters per second per second. That's something we can do. Yes, ma'am. For S, well, S is just going to be some function of t, right? So that's going to predict position as a function of time. Okay, what we know then, so Galileo or Newton or anybody we could observe this, that objects accelerate uniformly due to gravity, and we could even measure that. If we, like I say, if we were to take, when things fall straight down, they move pretty fast, but if we were to do like roll balls down inclined planes, we could kind of slow down the acceleration of gravity and make some good predictions. And we could come up with this. We could come up with the differential equation A equals 9.8. Okay? That doesn't look like a differential equation because it doesn't involve a derivative. But if we write A as the derivative of V with respect to t, now it looks like a differential equation. The acceleration equation for objects in free fall is that. It's really simple. It's always constant. If I drop something, the acceleration in free fall is always negative 9.8 because it's going down. But we won't even need to put the negative sign on if we don't want it. Okay, for this purposes. So then A is really dv dt, and so if I want to know what the velocity function is, how would I find it? What am I going to do? Because that's a differential equation. How do I, what's the solution going to look like to a differential equation? Okay, yeah, it's going to look like V equals something, right? So we're going to undo the derivative to reveal the velocity function, right? So we're going to play calculus Jeopardy. And later on, we'll talk about more of an algebraic way to approach this. But for now, we'll just play calculus Jeopardy. That really is what you're going to do. So what is the answer to this? V equals 9.8 t plus c, and we'll just call it c1. You might end up with other constants too. Okay? Agreed? Okay, now that's a function of t, isn't it? So I could even do this if I want to. just to remind myself that velocity is a function of the independent variable t, right? Okay, so that's pretty good, but there's something a little bit that's just not totally satisfactory about this. We don't know what this constant is, right?
Right.
Any suggestions as to how we could find a name for that constant? Is there a particular, t is our independent variable, is there a particular time that might be interesting?
Like when you start.
Okay, when I start, what's the time equal to when I start?
Zero.
It's at 0, right? So what if we were to say, let's let t equal 0? What does that do? Then we end up with v of 0 equals 9.8 times 0, which is what? 0. Plus c1. So what is c1 then?
0.
Well, no, it's equal to, the velocity at time 0 equals 0 plus c1.
Yeah.
So c1 is really just equal to the velocity at time 0. What do we call that in physics? Yeah, v naught, which is what? Initial velocity, right? What is what mean? Oh, okay, yeah, not just means sub-zero. Yeah, sorry, that just means when you have a subscript. So the way we would write this in physics, v evaluated at t equals 0. That means when I start the stopwatch, right? So that's the initial conditions. That's when we first start things off. And so we would just sort of write that as v sub 0 or v naught. Okay, so that's the meaning of c1. Now that's interesting because that tells us then that the velocity function is really v of t equals 9.8 t, which is another way of saying acceleration. But how about if we even just do this? I'm going to make one little tweak here so we get the exact formulas. What if we don't even pin ourselves down to gravity? What if we just do this for some constant acceleration, right? So we're just going to call our acceleration a. We're not even going to call it. We can later plug in 9.8 if we want to. But let's just say a equals some constant, which we're going to call a. See what I'm saying? How's that going to change things? Well, then every place we had a 9.8, we're now just going to write that as a, which is a constant. That's just some number, right? For our planet, for gravity, it's 9.8. But maybe we're accelerating a car uniformly at 3 meters per second squared. Any situation where there's constant acceleration is going to apply here then, right? So would you agree then that if this is a constant, let's just backtrack just a little bit. If I do the antiderivative, if I play calculus Jeopardy and a is a constant, isn't the answer a times t plus some constant?
Yes.
Agreed? And so then what do we get? Well, this was really supposed to be an a, but the outcome is the same. A times 0 is still 0. And so what do we get? Well, then we end up with v of t equals at plus v naught.
Yeah.
Does that look familiar, physics folks?
No.
That's kinematic equation number 2, isn't it? Right? Okay? So this is useful. This is what we call, this is a kinematics equation for constant acceleration that relates final velocity to initial velocity, acceleration, and time. And we use that a ton in physics, and people will attest to that are in physics, right? Okay, so let's go one step further. Let's go one step further and let's solve for position, right? So position is related to velocity this way, right? We know that velocity equals ds dt, right?
Yeah.
So we're going to trade the velocity for ds dt, and that equals v naught t plus at. Now v naught is a constant, right? Agreed? That corresponds to the initial velocity of our situation, right? Okay.
How did you get v naught?
Okay, because we got it right here. Because when we solved, we got our general solution for velocity was velocity equals at plus some constant.
Mm-hmm.
But we wanted to know sort of physically, what does that constant mean? And so we let t equals 0. So at t equals 0, v of t becomes initial velocity, v at 0, right? A times t went to 0, and so that told us that the only thing left over was the constant. So the constant is equal to initial velocity, which we just summarize by calling it v sub 0. That means v of 0.
We have a y in the dsdt equals
Oh, whoops, I got you. I see what the question was.
Okay.
That plus sign I took to be a t. It's not. There we go, like that. Sorry. There we go. Okay, much better. Thank you.
Mr. O'Leary,
Yep.
Can you explain what rule is that? What is V naught?
So v naught, so that would be, here's how we can use that.
Like what rule is that? I don't understand.
Okay, so here's a problem we could solve with that. We could say, let's say we have a car that's driving along at 10 meters per second, and it's going to accelerate at a rate of 3 meters per second squared for 4 seconds. How fast will it go? So then we would just say v of 4 equals the initial velocity, which I said was 10, right? 10 meters per second plus...
Oh, so that's just some variable you
Yeah, I just plug stuff in, right. See, I'm just going to plug in all but one of those to solve for the missing one.
So V naught just stands for what you start, the
Yep.
velocity you start with.
Right, and so a lot of times an object will start from rest, so what would its initial velocity be? 0. Good.
I don't get AT, because I thought AT equals v sub 0.
No, v equals at plus some constant, but when we let t equal 0, then that term goes away, right? And then I end up with c by itself equals v when t is 0, which we just call initial velocity.
Oh, and then you just plug the AT back.
Right. And so now we found out what c is, and so all we're going to do is, once we know that this is the case, we just plug it in right there to get our answer. Okay? So now let's go a little further with this. So let's play this game again. Let's play Calculus Jeopardy again and do another antiderivative. So if we undo this, s equals what?
V naught t.
V naught t, right?
AT squared.
V naught t. Now what about this one? This one's a little bit tricky, right? What's the derivative of what is going to give us a times t? You got to really think about this.
T to the
T to the A.
No,
Oh, no.
a is a constant.
1/2.
Ah, 1/2 a. Right. Okay, check it. See if that works. Okay, hold on. Look at that. That one took a little bit of thought, and we're going to come up with some rules, just like we have rules. Hey,
I'm gonna just disrupt you.
Zoe?
oh, okay.
I'm gonna listen. Learn something.
Oh, okay, all right. So you know how we have rules like for doing derivatives, right? We know how to take the derivative of 5 or of x to the 5th, right? We know the power rule. Okay, we're going to come up with corresponding antiderivative rules, but we don't have them yet. So for now, we got to think hard. But you see how this works? If I differentiate this, the a is a constant. What's the derivative of t squared?
But there was no t squared before.
You're right. But this is the answer. We want to know what's the question.
Oh.
Right? We're asking the derivative of what term gives us that answer. So it's got to be a times t squared, but I have to include a 1/2 out front to cancel the 2 out when I differentiate, right?
Yeah.
Got it?
Got it.
Okay, plus, oops,
But we can have any plus v1.
plus C2 we'll call it. Some other constant, right? C2, just some other constant. Instead of putting it at the end, I put it out front. Just because I was running out of room over
Are we
here.
learning physics problems for this?
Well, no, this is, no,
It's just
You're not.
technical physics people understand.
you're not. This is just, we're just solving a differential equation to get an answer that's going to make sense to the physics people. But it wouldn't, it's not a big deal. You're not going to do this. Yes.
It's C sub 2 because it's a different constant.
Because it's a different constant from the first one. Right, exactly. So what are we going to do? Now, keep in mind that we could rewrite this. This is a function, right? It's s as an explicit function of t, right? Gives us that formula. So what do you think we're going to do to try to find the identity of that constant? Well, we just did that. This is our general solution, right? Set t equal to 0. Right, Hunter?
Yep.
Right? So have a look, please. So what do we get? If I set t equal to 0, then we get s of 0, which is probably means what then? S is position.
It's at the beginning.
Initial position, right. So initial position equals C2 plus V naught times 0 is 0, plus 1/2 times A times 0 squared is 0. So there it is. C2 equals initial position. So C2 equals S naught, not S naught, S naught. And so we end up with our final answer then, S of t equals C2 was S naught plus V naught t plus 1/2 AT squared. Does that look familiar, physics? Right?
Wait, but how do you equal, like, how do you get T equals B naught?
Okay, so we called them, in our stupid physics book, they called them D's instead of S's,
Oh, yeah.
but in every other physics book in the world, they call them S's.
But the first one, like, the one S equals S naught plus AT. Isn't that one?
Well, we had D equals D naught plus V bar T. Yeah. Okay, does that make sense? Somewhat, okay.
I'd rather use real calculus.
Yes.
Can we play real calculus, Jeopardy?
Yes.
Real cat.
Here's a question, hang on.
This equation means like the initial spot you start,
Yes.
starting at the initial speed.
Right, so this equation means,
So if both zero, then it'd just be 1/2.
yeah, right. So if you started from the starting line,
Like you're not moving.
right, you're not moving and you're starting from the starting line with your position is at 0, which would be a convenient thing to do a lot of times, then both of these terms would go away and your position function would just be 1/2 AT squared, where A is whatever your acceleration is.
But once you start moving, then you add those in.
No, these are the initial conditions, so those never change.
Like if you're
Those are the conditions when I start the stopwatch or when I start filming. Okay?
How can your initial position be anything more than
Well,
where
okay,
you started?
because let's just say we have to set someplace equal to 0 to mark position, right? So let's just say, for example, that this is going to be, I'm just going to move in a line. Let's say I'm going to call this the starting line,
Wouldn't
right?
that always be 0 because that's where you're starting?
Well, usually you can do that. Usually you can, but there are some situations, like I'll just give you an example.
So when you're on a cliff, it's not if wherever you're starting is always going to end up being 0.
Yeah, but sometimes it's not convenient. Here's a quick example. What if we had a cliff, and let's say that we're going to, you guys remember these kinds of questions. Let's say we launch a projectile up in the air off the cliff, and we want to know when it hits the ground. Okay, if we know that the cliff is 50 meters high, we'd know that the initial position is positive 50.
Okay.
See what I'm saying? And we want to know when the final position is 0. Maybe we're solving for t, or we're solving for one of the variables in this equation presumably is something we're solving for. Okay. Does that make sense?
Yes.
Okay. All right. So
Mr. Oil.
yes. Oh, okay. I'm gonna take a roll and we'll call that a day. But now you know how to do antiderivatives.
Wow, I've been learning that all year.
Yeah.